Hello, everyone. So the year is 1665, and a 23-year-old Isaac Newton is at Cambridge, but the Black Plague is raging across Europe. And so much like in our last pandemic, they closed lots of things down to keep people apart, and that included closing Cambridge University. And so Isaac Newton returned to his estate outside of Cambridge. This is where he did some of his most brilliant work. You see up here he was born on Christmas Day, at least under the previous calendar, 1642 to 1727. He was born the same year as Shakespeare and the year that Galileo died. So he's at his estate, right, outside of Cambridge. And he is kind of working on things, right? And he's sitting under this apple tree in his orchard, as you can see here in this GIF. And then, as the story goes, an apple falls from the tree. And Isaac Newton, being Isaac Newton, says, gravity is the force which made that apple fall from the tree. And if you notice in the GIF, he then looks up through the tree. See him looking up through the tree? And he thinks about the moon in its orbit around the Earth. Being Isaac, he knows that the moon, essentially moving in a circular orbit, must have a net force acting upon it, otherwise it would move off tangent to the circle. So this was the brilliant part. He said, maybe that force of gravity which causes the apple to fall to the Earth is the same force which keeps the moon in its orbit around the Earth. Now, this may not seem too surprising to you, but at the time it was revolutionary. Gravity was thought to be a terrestrial thing. Gravity was thought to be something that only occurred on Earth. Right? Now, Isaac Newton didn't discover gravity, as he's sometimes erroneously credited with that. Right? Rather, he extended the idea of gravity out, right, outward from the Earth. Galileo knew about gravity. Right? We talked about free fall, for example, which is falling under the influence of gravity only, and Galileo's law of falling bodies. But what Isaac Newton did is said, hey, maybe this force isn't just terrestrial. Maybe it's the force which keeps the moon in its orbit. And then he took it even a step further. And he said, maybe there exists a force of gravity between any two masses in the universe. Right? So he kind of took it into more and more of a general idea, right? And then went searching for how he could prove that that was true. And that's where we're going to come in here. So we are going to look at this force of gravity, right? And the things that Isaac Newton found affected the force of gravity. Right? And that would be the masses of the two objects. Call that the mass of object 1, which we'll call m1. Notice force of gravity is, of course, our old friend F of g. The mass of the second object, which we'll call m2. And then he also thought that the separation distance between the two objects might affect the force of gravity. And we'll go much more in depth into how this is all put together, right, in the post-lab. Right, but for now, we're going to look at force of gravity, the two masses, and the separation distance. And you notice we're going to use the classical r for separation distance, mainly because Isaac Newton was looking at the Earth and the moon in its orbit. And so the distance between the Earth and the moon is essentially the radius of the moon's orbit. Right? So we use an r here. You would see in some other books they might use a d for distance, right? Separation distance. But it's really from the center of one object to the center of the other object. Therefore, the purpose of this lab is to create graphical and mathematical representations of the relationships between the four variables: the force of gravity acting between the two objects, the masses of the two objects, and their separation distance. Now, this is a very, very hard lab to do in reality. It takes some pretty heavy-duty equipment and lasers and mirrors and some big lead objects. It's really hard to do because, as you're going to see, we get really small forces of gravity between small masses. right? So we need some big masses in order to measure this, or a really precise apparatus. And so we're going to get around that in here by using, of course, simulations. Right? And as you're going to see on your lab sheet, we're going to use two different simulations. Okay? In the simulations, we're going to be able to control the mass of object 1, we're going to be able to control the mass of object 2, and we're going to be able to control the separation distances. So these will all be independent variables. And then the simulation will tell us how much force of gravity there is between the two objects. This is a fairly complex lab, not only in doing it in reality, but even using simulations. With 3 independent variables, we have to do 3 different labs, because we can only change one thing at a time, right? So there's going to be 3 parts to this lab, and actually a 4th part, because the first part's going to look at something a little different. And then we're going to put it all together in the post lab. Okay? So the first simulation we're going to use is on the physics classroom. It's called a gravitational field simulation. Right? When you click on the link, which is on your schedule doc, right, you can open up the simulation, make it fill the screen, and you'll see that this is more of Isaac Newton's idea. Here's a planet, here's a moon, right, which could be in orbit with the planet. Here's a ruler to measure the separation distance. I'm not really too concerned with that. You're going to do some work with this simulation looking at the sizes of the forces and the direction of the forces, okay, that act. So you're going to put this in the middle of the screen. And you can see, when you move this around, you see how it changes the size of the arrow? Right? That's the force arrow. So you're going to put this in the middle of the screen. And then you're going to move this to different points around and sketch some arrows. Note, you can also click here and turn on the force of gravity acting from the planet to the moon, because after all, being Isaac Newton, he knew that if the planet pulls on the moon, what's the moon do? The moon pulls on the planet with an equal and opposite force. Right? So that's what we're going to use this simulation for. Okay? The next simulation is the one that we're actually going to get the numbers from. It's called a FET. Don't worry what that means. It's a, it's a physics simulation that we can use that are made out of, I believe, the University of Colorado. Again, this is a simulation which there's a link right on your schedule doc. So you'll notice here we have 2 objects, M1 and M2, just like we used in the lab, right? We can move these objects around, but unlike the last simulation, you can only go in one dimension. And they make weird noises. So here's a ruler which you can use, right, to measure in meters. It's pretty easy to actually put the ruler up there and move one, to different distances and be pretty precise with it. You can change the masses, mass 1, mass 2. And then the other thing I want you to notice is up here, it shows you an arrow for the forces, but it also lists out the force. And you'll notice that even when the masses are big and they're close together, these are really small numbers. There's not a lot of force of gravity, even on 2 1,000 kilogram masses. So to help you write these down, if you go down here and you click on scientific notation, we'll be using a lot of scientific notation in this part of the unit. So that's how we can control the separation distance. Right? Mass 1, mass 2, right? And then it will tell us the force. Okay? So that's the second simulation. You're going to do 3 different labs with this simulation. You have to graph, you have to linearize, right? And write down all the information and sketch the graphs on your lab page, right? And all that kind of thing. So it's another big, long lab. So enjoy this lab, which we're calling the Law of Universal Gravitation, because that's what we're eventually going to name the math model we get out of this, so named by Sir Isaac Newton.